Hello, good morning. I am SEEMA GARG, Associate Professor in Chemistry, SPC Government College, Ajmer. Today's lecture is on dienes. It is video 88, lecture 26. It is also referred as alkadines or diolefins. It is for BSc Part 1, Organic Chemistry, Paper 2, Unit 2. Dienes are classified into three classes. Cumulated dienes, that it having two double bonds are adjacent to each other. For example, 1,2-propadiene, that is also referred as alene. Conjugated dienes, two carbon-carbon double bonds are separated by one carbon-carbon single bond. For example, 1,3-butadiene. Isolated dienes, two carbon-carbon double bonds are separated by more than one carbon-carbon single bond. For example, 1,4-pentadiene. Relative stabilities of dienes. Cumulated dienes. Cumulated dienes, when it hydrogenated with 2 moles of hydrogen, it will give normal pentane. And it will evolve minus 70.5 kilocalorie per mole energy. Delta H value is minus 70.5 kilocalorie. Whereas 1,4-pentadiene, isolated diene, when it is hydrogenated in presence of platinum, it will form normal pentane and it will evolve minus 60.2 kilocalorie per mole energy. 1,3-pentadiene, that is a conjugated diene. It is on hydrogenation in presence of platinum. It will form normal pentane, and delta H value will be minus 54.1 kilocalorie per mole. We know that the stability of the molecule is inversely proportional to delta H value. See, here the delta H value of conjugated diene is the least value, means it having 54.1, whereas cumulated diene having 70.5 kilocalorie per mole. So it is less stable. Cumulated diene is less stable. Conjugated diene is the most stable, and it is more stable compared to isolated diene and cumulated diene. So on the basis of hydrogenation energy, we can find the stability order of the molecule. Methods of formation. Preparation of cumulated dienes, alene. It is prepared from 1,2,3-tribromopropane when it is dehydrohalogenate. In presence of KOH, it will give this dibromo product, and on further dehalogenation in presence of zinc methanol, it will form alene. From terminal alkynes, propyne, when it is heated with alcoholic KOH, it will form alene. From haloalkenes, see here, this one haloalkene in presence of OH, it will form alene and HX. 2-halopropene, when it is dehydrohalogenate in presence of base, any OH, it will give alene. From alkenines, when it is reacted with hydrogen halide, it will form 1,4 addition product and it will give alene. From dihalocyclopropane, when dihalocyclopropane is heated with magnesium, it will form alene. Preparation of conjugated diene. Dehydrohalogenation of butane. Thermal dehydrogenation in presence of chromium oxide, aluminum oxide at 600 degree centigrade temperature, it will first give mixture of 1 butene and 2 butene. And on further dehydrogenation, it will give 1,3-butadiene. Pyrolysis of cycloalkenes, it is a retro-Diels-Alder reaction. Cyclohexene, when it is heated with nichrome catalyst, it is a mixture of nickel, chromium, iron alloy. It will give 1,3-butadiene and ethene. It is a retrosynthesis. Dehydration of diols. 1,3-diols or 1,4-diols when in presence of sulfuric acid, when heated, it will form 1,3-butadiene. Dehydrohalogenation of halohydrocarbons. 1,3-dichloro-3-methyl-butane, alcoholic KOH. It will form 2-methyl-1,3-butadiene. It is also referred as isoprene. It is a very important product for polymer preparation. From acetone, when acetylene is reacted with acetone, and then on further partial reduction, it will form this product, and on heated with aluminum oxide, it will form isoprene. Preparation of isolated dienes. Dehydrohalogenation of dihaloalkanes. In presence of alcoholic KOH, it will form 1,4-pentadienes plus 2 HBr. Wood's reaction, when allyl chloride is treated with metallic magnesium in ether, isolated diene 1,5-hexadiene is obtained. See here, 1,5-hexadiene. Structures of dienes. The structures of isolated dienes is similar to that of alkenes, but the structures of cumulated dienes and conjugated dienes are somewhat modified by the interaction of two carbon-carbon double bonds. Structure of allenes, cumulated dienes. See the structure of allenes. It is a cumulated diene. It having 1 and 3 carbons. C1 and C3 carbon are sp2 hybridized, whereas C2 carbon is sp hybridized. So due to the difference in hybridization, its stability is also reduced and the bond length is also changed. As we know, the single bond length of double bond length of carbon is carbon-carbon double bond is 1.33 angstrom, whereas in allene it is found 1.31 angstrom. It is reduced. So due to the difference in the hybridization, its bond length is also reduced. Structure of conjugated dienes. 1,3-butadiene having stability due to all carbon atoms are sp2 hybridized. See here, all carbons are sp2 hybridized. And bond length is also changed here. As we know, this carbon-carbon single bond length normally it is 1.54 angstrom. But in 1,3-butadiene, it is reduced to 1.48 angstrom due to the partial double bond character arise due to the hybridization of sp2 hybridization of adjacent carbon, and double bond. Normal double bond length is usually 1.33, but here in case of 1,3-butadiene, it is higher, it is 1.37 angstrom. So it is increased due to this delocalization of pi electrons. Conformation of 1,3-butadiene, see here, it will give cis and trans form. Trans form is more stable compared to cis form. We can calculate the stability of conjugated dienes also. Heat of hydrogenation, conjugated diene, especially we will take here 1,3-butadiene. Heat of hydrogenation of 1,3-butadiene on hydrogenation evolved minus 30.3 kilocalorie per mole, 1 butene, right? So in 1,3-butadiene, it having two double bonds. So expected value will be 60.6 kilocalorie per mole. See here, 2 times. But actual heat of hydrogenation of 1,3-butadiene, practically it is found 57.1 kilocalorie per mole. So there is difference of heat of hydrogenation of 1,3-butadiene is minus 3.5 kilocalorie per mole. So we can see that 1,3-butadiene is stable by minus 3.5 kilocalorie per mole energy. So 1,3-butadiene is more stable compared to our isolated diene and cumulated diene. Thank you very much for today's lecture.